In this chapter, we're going to talk about the first approach to making nanostructures, which is top-down. That is, starting with a macroscopic piece of silicon, for example, and chipping away at it until one has a nanostructure. We'll talk about photolithography, which is the classic way of making structures from silicon, generally limited to micron-sized features because of the limit of optical resolution, but capable of nanostructures, even as I will explain. Electron beam lithography, which is a great way for doing one-off research structures on the nanoscale. Micromechanical structures, which may not be nanoscale, but are an essential part of nanotechnology, like, for example, atomic force microscope cantilever probes. Thin film technology, generally we'll talk about vacuum deposition systems, but also molecular beam epitaxia that we talked about in Chapter 1. Masks for making features using self-assembly. Focused ion beam milling, which is a wonderful way of making one-off nanostructures, and the stamp technology we talked about in Chapter 1. Finally, we'll turn to the subject of nanojunctions for electrical measurements. So let's begin with photolithography. In photolithography, a silicon surface to be structured might be covered with a layer of oxide that's to be etched, and then with a layer of a polymer resist, which I will draw like this, and then finally covered with a mask. Now I'm showing here a mask in contact with the structure, however it could just as easily be a mask that is remote from the structure and imaged down onto it, in fact more likely to be that way. The resist can operate in one of two ways. If we start off with a very high molecular weight resist and we expose it to energetic enough radiation, it can cause the backbone of the polymer to break, so that where the polymer is exposed becomes low molecular weight, and therefore when we flush a solvent over this after removing the mask, the polymer becomes dissolved away in the region exposed to the light. This is called a positive resist because it reflects the shape of the mask. Another possibility is that one has a fairly low molecular weight polymer that on exposure to light forms reactive species that cross-link, making the polymer into a high molecular weight polymer that is insoluble, and therefore when you remove the mask, the resist structure is a negative of the mask, like this. This is called a negative resist. Now, when you etch away the surrounding oxide, in the case of a positive resist coverage, you'll get a hole in the oxide like this. In the case of a negative resist coverage, you'll etch away the oxide everywhere except where it is protected by the resist. The full panoply of tools available in a typical clean room are, as I mentioned, oxidation. Typically a wafer is protected by growing silicon dioxide on it. This is readily etched away in hydrofluoric acid where it's not covered by resist. Masking, which I told you about, masking the structure so that you can selectively etch it. For electronic devices, one very often uses ion implantation. So, for example, silicon that has very few dopants in it can be made conducting by implanting boron or phosphorus to make either N-type or P-type silicon. Etching of the structure, I mentioned hydrofluoric acid etching to remove oxide, but there are various other types of etch, including, for example, potassium hydroxide that etches selectively along certain planes of the silicon. Metallization, which is the way of placing metal contacts on devices, and then lift-off, which is a rather splendid technique in which the surface to be metallized is covered with resist that is exposed at certain places, like this. So here is the silicon dioxide surface perhaps, and maybe you want to have a metal here. Well, the whole surface is coated with metal. And then a solvent for the resist flowed through. And what this does in floating away the resist is to break the metal at these points and leave behind a surface that is now selectively metallized. So these are all the tools of modern micro and nano fabrication. They go back, though, to the earliest days of electronics. Panel A shows the first point contact transistor developed by Bell Labs in 1947, and that object holding the point contact on really is a paperclip. Panel B shows the next step in the evolution of semiconductor circuitry, which is the integrated circuit. Jack Noyce at Texas Instruments and independently Robert Kilby at Fairchild realized that not only could you make a transistor from semiconductor components, but by putting, for example, a thin strip of silicon as the contact to this transistor collector here, one could also make a resistor. There are ways also of making capacitors and the analogues of inductors, and so these days very complicated circuits can be put together completely with lithography and with no need for independent wiring. The Intel Pentium chip that you see at the bottom here has features as small as 65 nanometers on it and about 500 million transistors imprinted on it. So how do you make features as small as 65 nanometers using optical lithography? One way to do this is to use a very short wavelength, and Excimer lasers can provide wavelengths down into the range of somewhat over 100 nanometers. This means that with a high numerical aperture lens, features as small as 50 nanometers or so can be etched. One of the limitations is that lenses for focusing light down to such small features as this doesn't have significant range on the surface before it goes out of focus, and so for that reason a very specialized lens will be used together with a stepper that moves the device so the pattern can be exposed repeatedly over the surface without the need for wide field optics. Here are some examples of electronics made by lithography. The first example is almost trivial. It's a PN diode, and in this case all that has been done is to take an N-type semiconductor and then to dope it, in this case with hole donors that make it P-type, and at this point with electron donors that make it N-type, but very heavily so that it's a good contact, and this gives a diode PN junction. By building structures like this up in three-dimensional steps, one can make very complicated devices, as in, for example, this CMOS, which stands for metal on semiconductor circuitry, and complementary metal on semiconductor circuitry, and here you see layers built up with metallization contacting various transistors inside the structure. In the next module we will talk about electron beam lithography and other nanoscale tools.